Well, hello there and welcome to the 12th lecture of this short course called Behavioral Theory of Systems with a View Towards Data-Driven Control. So in the last few lectures we actually proved a very interesting result. What we have proven is that as long as I'm looking for trajectories in the space of C infinity functions, if I have two behaviors, one given by the kernel of R psi and the other given by kernel of R tilde psi. The two behaviors are equal if and only if the row spans of these two modules of these two matrices, the kernel representation matrices, are the same. So B and B tilde are equal if and only if R is equal to R tilde. Okay. Now, so this means that if I now look at behaviors which are subspaces of C infinity R Q, right. So all those behaviors which are C infinity behaviors given by these kernel representations, then to this I will be able to attach a module, right, a submodule of let me write it 1 cross Q so that it's clear that we are looking at the row modules. Okay. So to teach each of these behaviors, I can associate this equation module uniquely, you see, because no two different modules can give rise to the same behavior, right. Because if the two row modules are different, then their behaviors will necessarily be different, because if they are equal, the row modules have to be necessarily equal, right. And likewise, if there are two different behaviors, then their corresponding modules will also be different. Their corresponding equation modules will also be different, right. And it has something to do with this C infinity, some property of the C infinity. As you have seen before, that if the functions are not C infinity, then this need not be true. Yeah, like as I have already mentioned before, with C infinity compactly supported. Likewise, one can think of things like L2 functions. I am sure you are aware of these notations, L2 functions, L2 from R to R. What does this mean? This means this is the collection of all those functions W which are mappings from R to R, which have the property that if I do this integral, because it's just I can just take mod squared, yeah, this is finite. Yeah, these guys are called finite energy functions or L2 functions. So we can look for solutions in L2 functions as well, provided we allow the ideas about differentiations for L2, which requires us to go to distributions and so on. But for the time being, it is enough to think about systems which are, let's say, at least once differentiable trajectories which are L2. In that case, suppose I look for solutions of this d dt plus 1, right, W equal to 0. We all know that the only solution that I get from this guy is that Wt must be equal to e to the power minus t W0, isn't it? That is the only solution that you get. And is this finite energy? Of course it is not. You can try and see that finite squared energy, is it like that? It certainly does not have finite. This square from minus infinity to infinity certainly is not less than infinity. So this guy does not belong to L2. So the only solution that is of L2 that also satisfies this differential equation is when W is identically 0. That is the only solution. Of course, if you take 1 times W equal to 0, that also has this solution. So then two different row modules, two different kernel representations, different as in this is a kernel representation, the module that it spans is this, and this is another kernel representation, the module that it spans is this. Of course, this is strictly contained in this one, right? So therefore, two different modules, same behavior. So things like this can happen if you are not careful, but if you allow your functions to be only smooth functions, then there is no escaping. The behaviors will be equal if and only if their row modules are equal. Two different row modules cannot give rise to the same behavior. I cannot overstate the importance of this result. Yeah. To give you an idea how important this result is, at least for the kind of things that we are going to be dealing with, let us think of this experiment, this question, where it's a question which is of central importance for data-driven control. Suppose, so what we usually see in our control systems related studies, that we already have the model, right? We know the equations and we are looking at the solutions, and we are based on the equations we are trying to design a controller for the system, and that's the usual approach. What if we ask this question, that instead of the equations, I have a few trajectories that I know are coming from that system, and we ask this question, that what are the system's equations that give rise to these trajectories? What are the equations, what are the laws that explain this data? Yeah? So data instead is given. Data given means that I have information about a few trajectories. Information about one or more trajectories. Right? From there, I want to find out laws or equations that explain that data. Or in other words, this is a phenomenological kind of a question. The experimental results are there. What are the equations that explain that data? What are the laws that explain the phenomenon? To give you an example, let's say we have e to the power minus t. We have observed that the trajectory is e to the power minus t. We have observed that this is my w hat t. There is a black box. I am measuring the output, and I have observed that sorry, I should write w. I have observed that one particular instance of this wt is this w hat t, which is k e to the power. Let's say this k is some number, say 2 e to the power minus t. What is the law that will explain this? So if I assume that my system is given by a linear ordinary differential equation with constant coefficients, can you tell me what is the equation that explains this data? Obviously, just by looking at it, you know that the system's equation must be d dt plus 1 w equal to 0. What gave you this idea? Because this looks like, we know this form, it is e to the power minus t times w0. It is this form, right? And this form is, we know from formula that this is what it must be, right? So in other words, what we are doing is we are asking this question that, okay, instead of one trajectory, suppose I have multiple trajectories. Suppose I have a set B. Notice that this is different from my behavioral notation. Yeah, behavior is this Gothic B, but this is a scripted B, right? Because it's not yet a behavior. I don't know whether it's a behavior. I don't know whether it's the kernel of something or not. This is some collection of some trajectories, W1 hat, W2 hat, some collection. And I ask this question that I find out a R xi. These W hats, each of these Wi hats perhaps is coming from a C infinity, is a C infinity function of size q. Okay? And I am asking this question, can I find out a row vector, yeah, a row vector of size q such that R xi, when acts upon these trajectories, takes them to the 0 trajectory for all I. Yeah, so that means R xi, this vector R xi, annihilates the set B completely. R xi annihilates, that's the technical term that is used here, annihilates B completely, yeah, because every trajectory in this set is taken to 0 by this guy. So, it is an annihilator. Okay. Now, I can look for such annihilators and I can collect them together, right, and I can use this notation A of the set scripted B, that is the collection of all those R xi's which are row vectors such that okay. What can you say about the structure of this annihilator set? The annihilator set is a submodule of R xi 1 cross q. Can you check that? Well, in fact, it's very easy to see. When is something a submodule? If it's a module in its own right. And what is a module? As we know, a module is like a vector space over the ring R xi. That means it must be closed under addition and closed under scalar multiplication from the ring R xi. Let us see whether that's true or not. Suppose R1 xi and R2 xi are there in A, B. Okay. Now let me write it properly. R1 xi and R2 xi both are, let us say, annihilators. If both are annihilators, then R1 xi plus R2 xi, when they typically act on a arbitrary W hat from B, what happens? This, because it is a differential operator is a linear operator, so it is distributive. So, that means this is equal to R xi W hat plus R2 xi W hat, right. But individually this guy is 0, this guy is 0. So, this guy must also be 0, which means R1 plus R2, R1 xi plus R2 xi must be there in the annihilator set. So, it is closed under addition. Likewise, suppose alpha xi is any arbitrary element from R xi and small r xi is a typical element from the annihilator set. Now, what happens to an arbitrary trajectory W hat when it gets acted upon by R alpha xi R xi? You see, this R xi acting on W hat is 0, whether there is alpha xi or not does not really matter. So, this is 0. So, which means then alpha xi R xi must also be an annihilator. Great, no? So, annihilator is indeed closed under addition and closed under scalar multiplication, which corroborates the fact that I had just mentioned, that this is a submodule. Great. It's an annihilator submodule. Okay. So, because it is an annihilator submodule, I can ask the question, what is the behavior that is associated with this guy, right? You see, when I have this annihilator submodule, yeah, it is a submodule of R xi and it is known that this module is what is known as a Noetherian module, a technical term that is used to describe such models. And a Noetherian module has the property that every submodule of a finitely generated Noetherian module is itself, they themselves are finitely generated. So that means this guy must also be finitely generated. That means I should be able to find out a matrix R xi of size R of size G cross Q such that the row span of R xi, that is the row module generated by the rows of R xi, is equal to this AB. Yeah. Okay. So then if that is so, what is the behavior that is associated with this module? The behavior that is associated with this module, denoted by B of the annihilator. What is this? This is by definition the collection of all C infinity functions such that R xi W equal to 0 for all R xi in the annihilator set. That of course is nothing but kernel of this R xi, right? So these are the equations. You can easily check that this is true because because if W gets killed by every row of R xi, then W obviously gets killed by every linear combination of the rows of R xi, but linear combination of the rows is what forms this annihilator module. So you see, we started with a collection of trajectories, namely this B. We looked at its annihilator module, and then we looked at the behavior corresponding to the annihilator module, right? What can we say about this behavior? This behavior certainly contains this set B. B was C infinity functions, right, which were such that the way I formed this annihilator is that the annihilator, the elements of the annihilator kills every element of B, correct? So those trajectories W hat, they are killed by everything in AB. But if they are trajectories which are killed by everything in AB, they by definition they should belong to this behavior. So that's why this containment is there. Are they equal? Well, not necessarily, not always, because this has the structure of a behavior. This, remember, need not have the structure of a behavior. This is just a collection of cells, right? Are you sort of surprised by these things? A little flustered perhaps by these things, but you should not, you should not be, because this is something that is very familiar to you. This is in fact directly analogous to this situation. You see, suppose I am looking at Rn. Yeah, I am sure you are aware of this notation. This is the Euclidean n-dimensional vector space over the real numbers. In this vector space, suppose I start with an arbitrary set alpha, just a set, and then I look for U often denotes an open set. Let me use the set, this notation S. S is an arbitrary set S, yeah, and then I look at the orthogonal complement of S, right? S perp. What is S perp? S perp is the collection of all those vectors, vectors V in Rn, such that when you look at the dot product, that is VW, which is by definition V transpose W, is equal to 0 for all what? For all W in S, right? Yeah, that's what S perp means. What does it look similar to? It looks exactly similar to the annihilator idea, no? What are annihilators? Annihilators are all those row vectors which kill those trajectories. Row vectors acting on trajectories are like dot products, not exactly. Don't quote me on this that they are dot products. They are not, certainly they are not. They are two different kinds, right? Here both of them are vectors, but there they are trajectories, column vectors, and row vectors are polynomial differential operators. So they are different kinds, but in a way they are similar, because like this V and W, when you take this dot product, you can view it as if a row vector V, or rather V transpose, is acting on the column vector W through this multiplication, this dot product. And under that action, yeah, it is similar to, it is analogous to what we are doing with polynomial differential operators. Now, if that is the situation, this is analogous to annihilators, and then when I go back to trajectories from the annihilators, that is like taking double pup, right? You are looking at all those W tildes, which are now such that V times W tilde, V dot product, is equal to 0 for all V now in S pup. So we are looking at a double pup, and it is very well known that the double pup always contains S. In fact, it is not just any arbitrary containment, it is in fact the smallest subspace that contains S. So the S double perp in fact is the smallest subspace that contains S. Well, that in fact tells us that when we have this containment, this behavior in fact is the smallest behavior that contains B. Lovely, isn't it? Well, if that is so, that actually is good for us, because why? You see, often these trajectories are coming from a system. If they are coming from a system, then it has a behavior, right? Of course, this B is a very weak imitation of the behavior, a weak copy kind of a behavior, because it's not even a behavior, it's just a collection of trajectories. But then when I look at its annihilator, I actually have obtained the behavior, the smallest possible behavior that contains this kind. As we will see later, that such a thing will be called the most powerful unfalsified model, MPUM, of these trajectories, of this data, right? This will be immensely important for us. But now, why did I broach this subject in connection with what we have proven, the last theorem? Now you see, suppose instead I start with a behavior. Suppose I start with a behavior. Then I look at its annihilator. Oh, let me write it properly. It's becoming a little weird. So suppose I start with the behavior B. So behavior given to us. And then from that behavior, I obtain its annihilator. I obtain its annihilator module, right? And then I obtain its corresponding behavior. What should I get? I should get back B again, if I'm dealing with only C infinity functions. Why? Because of the uniqueness, right? Because this was already a behavior, there is a unique module, right? There is a unique module that is associated with this behavior, whose behavior must be this behavior. Yeah. Now, what is that module? That module kills every trajectory there. Okay. So, in general, when I look at this annihilator, so what is, suppose the behavior, the row module that is associated with this guy is denoted by R. So AB in general must be contained in this, right? Yeah, this is what in general should happen, because we know that every trajectory in the behavior B gets killed by R. That's how R and B are related. This is the row span of row span of some r xi, and B is equal to kernel of r xi. So you see, everything, every element in this row module must kill every trajectory in this behavior. So obviously these elements here, the elements in this guy, that is in the row span of R, must be there in the annihilator set, right? So therefore this is what must be. But you see, when I go back to its behavior, when I look at the behavior corresponding to this guy, this must be this same behavior. Yeah, because remember, what is this BAB? BAB is the smallest behavior that contains B. And what is the smallest behavior that contains B? B itself is a behavior, so it must be equal to this behavior. So the two behaviors are equal. This guy corresponds to the row module R, it's given by the kernel of R, and this guy corresponds to, let's say, some R tilde, which is this AB. But what does our equality say? As long as the trajectories are C infinity, these two modules must be equal. Right? So therefore, by doing this, I actually obtain this R. Yeah, what does this mean then? This means even when I don't know the equations, even when so suppose there was a system, suppose there is a system, yeah, which is such that the behavior is equal to kernel of R xi, and I don't know this R xi, I have no information about this R xi. But I have information about this B. Suppose I have some trajectories and I know that the trajectories are representative enough that they span this whole B, yeah, whatever that means. Some trajectories are there, yeah, and I know that the smallest behavior that contains those trajectories is my behavior, is my system. So then from there, if by hook or crook somehow I can identify its annihilators, then I am sure that this annihilator set is nothing but the row span of R xi. Or in other words, if I can find out a generating set for this guy, suppose R tilde xi, such that row span of R tilde xi is equal to the annihilating set, yeah, then I am sure that R tilde xi and U xi must be related by a unimodular matrix. This comes as a big help because if I have some data about the system and I make the assumption, listen very carefully, I make the assumption that my system is the smallest behavior, the smallest system that explains this data, then for me to identify the system, it is enough to identify the annihilators of the data. And that is precisely what we will be doing when we are doing data driven control. We will be trying to identify the annihilators of the system, annihilators of the data. Okay? Now, we will put a stop in this discussion now. We will move to another very important topic, namely the idea of elimination. Before that, we will need to understand what is the meaning of this elimination, which will require us to know what are these variables which are worth eliminating. Yeah, that will take us to these various different kinds of representations or models, namely autoregressive models, autoregressive moving average models, just moving average models. Yeah, these are the three different kinds of models that we will discuss, and we will see what is the idea of elimination in connection with these representations, and then we will understand, we will try to study this very important theorem called the elimination theorem, which comes via what is known as the fundamental principle of algebraic analysis. Okay? These and many more is what we are going to see in the next few lectures. Till then, take care of yourselves. Bye.